All right, so by now you guys have all masked your either eggs or carrots after they've been soaking in that solution for that 24-hour period, and you obviously should have seen some changes in masses, right? Yeah. And some may be very dramatic changes. So a lot of you are saying, something's gone wrong, or, well, maybe not. Maybe your data is what your data is, and you can't say that it's right or wrong. Something happened, and now you have to observe what you think happened, okay? So we're looking at what process occurring here with our eggs and our carrots. What process are we observing? Okay, passive transport, yes. What kind of passive transport? There's more than one.
Diffusion, osmosis, ion channels.
Okay, so we're saying diffusion, osmosis, ion channels. We're just throwing everything at me right now. Diffusion, osmosis, and ion channels. Is it all of it? Is it some of it? Some of it? Okay. So, first of all, diffusion. How can we define diffusion? It is an active or a passive transport process. It is a passive transport process. What other passive transport processes did you read about? We saw diffusion. Osmosis, I heard. Anything else? Ion channels are not passive transport.
Why are they in the passive transport section?
They're not.
Oh, it's facilitated diffusion.
Facilitated diffusion. Okay, so we have 1, 2, 3 processes. Both of these are cells that probably really aren't alive anymore. Okay, they're not living cells anymore. Those chicken eggs were living, and the actual site, so when you look at your egg, okay, and there's the yolk, there will be a tiny little dot on the yolk, and that's the actual egg cell, okay, called the blastodisc. So it's a tiny little white dot. So if you have eggs this weekend, crack one, look at the yolk, look for a little white dot on it. That's the actual cell. The rest of the material, the egg white and then the yolk right here, is support material for the developing embryo. The eggs that we buy at the grocery store are not ever fertilized because the chickens are kept in cages or kept away from a rooster, so they never are going to be fertilized eggs. Even if you incubated them, they would not hatch into a baby chick. If you have chickens roaming in your yard, though, and you have a rooster, then you have to be careful. You collect the eggs and you put them in the refrigerator because you don't want them to develop in the event that they are actually fertilized. So, which one of these can we eliminate as not having observed? Well, let's first, I'm hearing different answers, so let's first make sure that we understand what is diffusion, okay? So let's make sure we understand what each one of these things are, okay? So, diffusion. How can we define diffusion? The movement? Movement of what? Molecules, any molecule, from a high concentration to a low concentration. Why do they want to move around? So they want to reach equilibrium. And equilibrium means that they all have enough space to spread out as far as they can, because they're constantly bumping into each other and ricocheting off of each other. Yeah.
If you, like we were talking about the fart in the car, when equilibrium is hit, does that mean that there's a specific ratio between the fart molecule and an air molecule?
No, because they're always moving. There's always going to be molecule-molecule collisions. They aren't going to stay because of Brownian movement. So I need you guys to make sure that you go back and you look either at the lecture posted on School Loop, or I don't think I put it in a Google Classroom. I think I just put it on School Loop on our calendar. And watch all of the video clips that are embedded in the lecture, because then you're going to get a better understanding of the concept of Brownian movement and the fact that molecules are always moving. There's vibrational energy. Even though something appears solid, the majority of the space at the atomic level is actually empty space. And so even though this table here is solid, the atoms are vibrating, the electrons are moving around. There's movement even in this, even though it's not perceptible at this level. Okay? So when you have liquids in solution, or molecules in solution, or molecules in the gaseous state, and they're not being held into some structure, like a solid is, where it's locked into a structural, a geometric configuration, then you're going to have molecules moving around all the time and bouncing off of each other. Diffusion, is this isolated to solid or liquids or gases or what? It's diffusion occurs in a liquid and in a gas. So our fart in a car, our idea of sugar dissolving in a cup of warm tea, the fact that I can put cream into my coffee, and without stirring it, it will eventually spread out throughout my coffee. You also have density issues, right? If the creamer is more dense than the coffee, it'll tend to hang out at the bottom. But if the coffee's nice and warm, those molecules are moving around at a rapid rate, and they're gonna bounce into the cream molecules, and they're gonna mix themselves around. How do we help that mixing of the cream and the coffee happen faster, though? We stir it. So then we're providing kinetic energy by actually stirring. We're moving the molecules around, increasing the rate of the molecule-molecule collisions when we're stirring it. And you guys all hopefully remember from the science you've had before about the rate that molecules move by temperature. What's the rate that molecules are moving around when they get heated up? Do they move faster or slower? Faster. So by applying heat energy, you make the molecules move faster. So a hot gas is going to diffuse faster than a cold gas. A hot liquid will diffuse faster than a cold liquid. Okay? All right. So were we observing diffusion here? Were we observing molecules moving from an area of high concentration to an area of low concentration? Yeah. But the next question is, well, what about osmosis? What's the difference between diffusion and osmosis? Yeah.
Osmosis is the transfer of water molecules between a permeable material.
Okay, so I'm going to use the word diffusion. Osmosis is the diffusion of water from high to low concentration. Now, in chemistry, you're going to see concentration referred to in brackets. So a nice shorthand way of referring to concentration is to put brackets around my arrows. From a high concentration to an area of low concentration. But now we're not just talking about fart, or we're not talking about fart gas or sugar molecules. What specifically are we talking about? We're talking specifically about water, and it has to be going through a membrane. But not just any membrane. What kind of a membrane? Semi-permeable. Or how about selectively permeable? Doesn't your book, does it say semi-permeable or selectively permeable? I don't know. One of those. Semi-permeable, selectively permeable, it means the same thing, right? But still you're having movement from high to low concentration. So, now let's talk about what limits osmosis. Okay, it's a passive transport process, which means what? When I say it's passive transport, what is significant about that? No energy is required. Which is good because these cells are now dead. So there's no ATP to help move things. They're just moving passively because of these random molecular collisions. Well, then what's moving? Here's my membrane. We're talking about osmosis. What's moving? The water. And so we're looking at the movement of water inside, outside, and which way are we going? How are we going to be able to tell which way the water is going? How are you going to measure the amount of solute? How are you going to know if water moved in or out? Yeah?
Like with the saltwater solution in the egg, since the saltwater, there was already salt in the water and it was all salt and whatnot, the water moved into
How do you know that the water moved in?
that and made the egg bigger.
It made the egg bigger. And so how did we quantify it? No. Quantify. How did we remember quantitative versus qualitative? When you say it got bigger, is that quantitative data or qualitative? It's qualitative because you're observing it with your eyes. You made some qualitative observations on your lab sheet. You should have below your data table about what those solutions looked like. Were they extra thick? Were they less thick? What was the appearance of the egg? But then you also took a quantitative measurement. Quantity means numbers. What numerical value did you collect? The mass. You had the mass before and the mass after. And what were you calculating on your data tables? Difference in masses and percent change. That will tell you whether something entered the egg or left the egg. Now, what that something is, do you know what it was? If it's osmosis, it's water. But do you know? Do we have a way to test that? Sorry. How nice. My phone goes off while I'm recording. Okay, so do we have a way to measure what's in those cups? Have we done any labs in here in which we measured and looked for the presence of a solution? Oh, iodine. What did iodine test for? Starch. Were we working with starches? Is there a starch in an egg? What's in eggs? Protein. So we can't use iodine to tell if there's protein moving. We'd use what? Biuret. So on Monday, I want us to test our solution and see if we can detect any protein outside of that egg. That'll be fun, huh? Okay. What else can we test for? Simple sugars. What did we use to test for simple sugars? Benedict's solution. So we could potentially test the inside of the egg to see if there was any sugar inside of the egg, right? Or we know if we put it in a sugar solution, there's sugar outside of the egg, so we don't need to test that. But we would want to test and see if there's sugar inside of the egg. Which molecule is bigger, a sugar molecule or a water molecule? Sugar molecule, right? Because if it's just a simple sugar, it's C6H12O6. It's much bigger. So I want you to think about molecular size and ability to get through a membrane. Okay, question?
Would we test for lipids too?
Would we test for lipids? Would you expect there to be a lipid in an egg? Yeah, I would expect there to be a lipid in an egg. And you know what? There might be starch in your carrot, so we could test the water to see if there's any starches in it. But also, since these carrots were shaved down from big carrots, I would expect that there would probably be starch on the outside of the carrot, and that would go into the water solution, and it would give us a false positive. The presence of starch in the water wouldn't mean that it came out of the cells. Just by rinsing that, the carrot soaking in there, I think it would get some starch. But I think it would be interesting if we weigh our eggs and carrots again after the weekend, and we look at if we see another mass change. In the meantime, for homework over the weekend, because we're getting close to the end of the period, I want you to start with a rough draft of those conclusion questions, which is on the back. They're on the back of your lab data sheet. And start thinking about those application questions. Start typing it up, knowing that it's a rough draft and you might get some more information on Monday that might change your mind a little bit. Okay? And in addition, can you maybe work on your Cornell notes for 5-2 active transport? We'll get a jump on that. Okay? And I'll put up on the table of contents. Your notes are gonna go on your next right-hand page in your interactive notebook, whatever that is. What is the next right-hand page in the notebook that's available right now?
51.
We think it's 51, 52. Yeah, it's an even number because it's a right-hand page, right? Our right-hand page is always even.
Yeah.
Yeah. So it's page 52. So those notes are already up with the 5-1. All chapter 5 is together. So maybe get a rough idea of active transport processes. I think our bell is about to ring. No, 9:52. Oh, wait. Oh, I still have time. It's
Friday.
first period, right? So we're not out of here until 9:52. Okay, so I have just a couple more minutes. I don't have to feel so rushed. So, just so you have a full understanding, do you have your data tables out? Look at your data table. On the one side, below your data table, I want to see qualitative observations of what each of your eggs or your carrots look like. You touched them. Did they appear different? Did they feel different? Was your liquid different? Okay, I want qualitative, and then you have quantitative numbers. You have numerical values there as well. On the back side of that paper, you have 6 questions, and you're going to do a very detailed explanation and as you answer each of these questions. I want you to keep in mind that every time you answer a question, you are making a claim. You are making a claim. Your claim is your answer. Okay? You must support your claim with evidence from the lab. Either evidence from the lab, so that could be our data, that could be observations, and that can also be what you know from your reading. The third thing that you're going to use every time you answer one of these questions is reasoning. And your reasoning is going to connect. You're going to connect your evidence to your claim. How does the evidence support the claim? This is a big missing piece that I see in your writing. You say something, but you don't back it up. So I want claim, evidence, reasoning. I want to be able to see that you've written your answer, you've made a claim, how are you backing it up, what evidence do you have to support your answer, and then why does that evidence support your answer? Okay? Claim, evidence, and reasoning. So in science, we always have to have evidence and be able to connect it. It has to be good sound scientific evidence. So nothing is due on Monday. Do you understand?
Yes.
We're doing a rough draft. You can bring that in, print it out, bring it in, and make some handwritten notes on it. And then we'll proceed. We'll weigh our eggs again and stuff. Okay? So I'm signing off. Listen to this again at home after you've forgotten everything. And you go, what did she say? What were we supposed to do? Oh, wait, I can go to Zitterkopf Science. So make sure you subscribe and like and leave me comments. All right, bye.